So welcome to the webinar today, guys. My name is Megan Guidry. If you don't know me, I am training lead here at NeSI, and our webinar today is about graphics processing units, or GPUs. Specifically, if you should be thinking about using them for your research. We have Wolfgang Hayek, NeSI and NIWA research software engineer on the call, who in just a moment will be explaining to us what GPUs are, what type of research they're good for, and what you can do to get started using them. But before that, I have a few housekeeping items, the normal webinar stuff. So we will be done well before 1 o'clock, most likely, but have time for plenty of questions. So do ask away if you have questions. That's what that question document is for, which I'm going to post again in the chat, the link to the question doc. So if you do have something you want to share during the webinar, there are two options for you. That question document that I have just shared, pop your ideas in there. We have some people monitoring that document, and we'll either type a response or we might verbally answer it in the webinar, just depending on what's easiest. Or you can share your comments and questions verbally after Wolfgang is done with his slides, with his presentation. And as always, if you're not actively speaking, make sure you keep your audio on mute so that we can reduce the background noise. And last thing I want to tell you, the webinar recording and materials will be available on the NeSI website in the next few days. And if you registered for the webinar, you'll get an email kind of alert once that's uploaded. So that's all from me. I'm going to stop sharing my screen and let Wolfgang take over. I think you're muted, Wolfgang.
Oh, okay. Sorry, I clicked on it, but unfortunately I didn't manage to mute myself. Okay, now, yeah, well, thanks, Megan. So thanks for the introduction, and also thanks to everyone who's on the call today for joining us here for this webinar. I'll share my screen right now. Okay, so now you should be presented with the title slide. So we gave that webinar the beautiful title, What to Know About NeSI GPUs. So the idea was to give you a bird's eye view of everything GPU. So I'll explain a bit what GPUs are, as Megan said already. I won't go into great detail, and I guess most of you will probably know what GPUs are, but just to get everyone on board, I'll start with that. And then I'll go on a brief tour around what GPUs are good for, and how you can get access to them, how you can program them, and so forth. I'll try to answer the question, should you use GPUs for your research, a little bit. I think the brief answer is yes, if you can, and I'll explain a bit more about that. And I'll also give you a sneak peek on the fabled A100s, so the latest generation NVIDIA GPUs that will be coming to NeSI very soon. So it'll take me about something like 20 to 30 minutes to go through these slides, and then I will have plenty of time for a discussion later if you have questions. Okay, once again, a brief overview. So a quick introduction to GPUs, if you haven't heard about those, and then how you can use them, what kind of GPUs we have for NeSI, and how you can get hold of those. All right, so as Megan said, a GPU is a graphics processing unit. So the idea dates back to at least to the 1990s. So they've been around for quite a while, for more than 20 years. And as the name suggests, they were designed originally with graphics in mind. And so graphics processing is a very particular application where you have to apply the same operation on lots and lots of data. So if you think of a screen full of pixels or an image with, I don't know, a few megapixels, you have to go through each and every pixel, and you have to apply the same operation to every one of them. And so the idea then was born to create a special piece of hardware that is very good at doing that. So the CPUs of the time were all serial, so they would compute one pixel after the other. And the GPUs are highly parallel. They are constructed to process many of these pixels at the same time. The big difference is that they do that at much lower frequency. So a typical CPU these days will run at 3 gigahertz, something like that, depending on the application. It can be anything between 2 and 4 gigahertz. A GPU will be much below that. So a GPU will run at 1.5 gigahertz, something like that. So it's only half as fast on that level. There's also a very important key ingredient in CPUs, which is called the cache. So that is a small piece of memory that is closely attached to a CPU and that delivers data very fast to the CPU cores. Because simply CPUs are so much faster than memory these days, so you have to use these caches to bring the data closer to the CPU. And for a GPU, these caches are much smaller. And I'll go into that in a second again. Because GPUs run more slowly, and the die space that you have. So when you physically construct these processors, you have to decide how you spend your silicon, and the die space on GPUs is almost entirely spent on compute cores, whereas on the CPU you have to make space for the caches. And so a GPU cannot be used as a general purpose processor. So you will not find a computer that runs only in the GPU. The GPU is a specialized thing, so it is always a coprocessor. It can be integrated into the main CPU. So you'll get that on your smartphone, on a laptop. You get a little GPU that sits on the same physical piece of hardware next to the CPU. And for NeSI, we have external GPUs, so they run as coprocessors on external cards. Okay, so just to drive the point a little bit more, what the difference is between the CPU and the GPU, I'll give you a famous quip from Seymour Cray. So the Cray who is behind or was behind the Cray supercomputing company. And I think that was in the late 80s or so, where people had the discussion already. So shall we use a few really strong cores for our compute, or shall we go and build lots and lots of cheap cores that we put together and run our compute on that? So the idea is not actually very new to do this kind of things. And Cray said, if you were plowing a field, which would you rather use, 2 strong oxen or 1,024 chicken? So, and I think Cray said that because at the time, Cray was involved in developing their own specialized HPC processors, and he obviously wanted to say, okay, buy our processors. They're few but strong. Don't go for the chickens. But now, a good 30 years later, we are actually using the chickens, and the chickens win in many fields of computing. And so here on this slide, you can see 2 die shots. So these are microscopic images of a CPU on the left, the GPU on the right. It's not the latest hardware, so these things are probably a good 5 to 10 years old, but the idea is still the same. So on the left, we have the CPU. So we have the oxen, which are on the one hand, the compute cores. You get 6 of those, so that's a consumer grade CPU. And have a look at how large the cache is on this die. So a lot of the die space goes into this fast memory that you need to drive the or to feed the CPU cores with data. And on the right-hand side, we have the chickens. So here, most of the die space, so these green areas, go into compute cores. So these are little compute cores, not very powerful, but lots and lots and lots of them. So thousands, literally. And the cache area is much smaller. So the cache area is in the center here. So the GPUs come with a cache, but not anywhere near as much. Okay, so what kind of applications have been run on GPU? Well, graphics processing, so no surprises here. That's what the GPUs were designed for. So most of you have probably heard of OpenGL, Vulkan and the likes, DirectX on Windows. So this is very well known for gamers or people that do visualization stuff. Gamers will also know that GPUs run the physics models to make the games fast. And pretty early on, so probably at least 15 years ago, when GPU hardware became more widely known, scientists realized that these things are also very good for scientific computation. Because say when you when you run a simulation where you solve physical equations, you often have that scenario that you have a field of data, so many degrees of freedom in an electric field, say, or in water flow or whatever you simulate. And you have to apply the same operation to all these degrees of freedom. So that's what you do in computational fluid dynamics, or CFD, for example, but also in material science and other disciplines. And so it turned out GPUs are really great for this kind of compute. Then there's signal processing. So if you're into say radio frequency technology, software-defined radio runs very well on that. Then image manipulation, of course, runs very well, say Photoshop and the likes. Then video editing software, and of course, very important use case is machine learning. So I think it's fair to say that the recent advances around, say, natural language processing and categorizing cat images online and these kind of things that has largely been driven by GPU power that accelerates neural networks, so deep learning and the likes. GPUs are also used for genomics, so in the bioinformatics discipline, and of course, you can also use them for things like self-driving cars and robotics. So these are important fields of application. Okay, so thinking again about whether or not scientists should use a GPU, and I think so. My take would be yes. So if you can use a GPU, you really should, because it will give you a really good boost in your computational performance. However, it does not really fit all potential kinds of scientific work that you could do. So if you have a lot of numerical work to do, and if that work comes in large batches, so and by batch meaning of handing over that workload to the GPU in one instance, then yes, you should definitely use a GPU, provided you can do that in its computation in parallel. If you only have little amounts of work, or if you have large amounts of work, but everything comes in very small batches, then GPU is probably not for you. And the reason is that because the GPU is a coprocessor, you have to switch context every time. So so you run something on the CPU, you switch over to the GPU runs its thing, then goes back to the CPU. And every time you do that, you have to wait a little. It's not very long. It's somewhere in the milliseconds or maybe even microseconds or something like that. But if you do that a lot, it starts accumulating. And so it's only really worth going to the GPU if you have a lot of things to do for it. There are also additional overhead costs for transferring data, because GPUs unfortunately have a separate piece of memory, so you can't use main memory directly. The data has to flow to the GPU first, and that incurs overheads and so forth. However, one thing to keep in mind is that, first of all, the world goes more and more towards things like GPUs. So when you look at the latest supercomputers that are now being built, much of their compute power, if not by far most of their compute power, now comes from GPUs. And when you look at the system configurations that people use now, in the past, it was standard to use 2 big fat CPUs in each compute node. But now there's a trend to add GPUs and do away with some of the CPU power. So meaning that if you cannot use GPU, then the systems are not actually for you. You won't be able to run very fast on these. Also, all the latest processing designs all go parallel. So the GPU obviously, but the CPU as well. So you get more and more cores. Each core can do what is called vectorization, a very similar idea to what GPUs do. So you apply the same instruction to many pieces of data. And so that means that if you can express your scientific workload in a way that is good for GPU, you'll also be able to run pretty fast on CPUs and probably other architectures as well. A hurdle, unfortunately, is GPU memory. So not only that you have to transfer the data over to the GPU card, but it is also relatively limited compared to what you get on classical CPU nodes. So the latest iteration of GPUs now come with 40 GB or even 80 GB of memory, which is a lot. So it's probably good enough for a lot of applications or most applications. But if you have really large data sets where you need hundreds of gigabytes or maybe even terabytes, then you have a problem still with GPUs. So you have to think a bit about how you can get this to work. There are also alternatives to GPUs. Say the Google developed the tensor processing units, TPUs. We don't have those on NeSI, but these are very specialized things for machine learning, whereas GPU is now a fairly general purpose kind of thing, at least for workloads that can run effectively on these. Okay, so now, if I got you hooked and you're interested, so how do you actually go about running your software on the GPU? Okay, option number one. So that's the lazy option. So meaning that that's the hopeful luxurious option that you might have. Maybe your software package actually comes with GPU support already, and then you don't have to do anything. You just download a variant of the software that's GPU enabled, or you just flick a switch maybe in your configuration. Or in some cases, you can download a container. That's something that NVIDIA, one of the GPU vendors, recently started offering. So there's a container repository. A container is basically it's a kind of virtualization where you have an image of the software that you can download, and it comes with everything. So you just need to download it and launch it, and you run on GPUs. That's super easy for open source things like TensorFlow, PyTorch. In some cases, you may need to check your license because some vendors try to recoup additional cost for porting the software to GPU by asking for additional payments to the license. So that's something you may need to check. Option number two, which is almost as easy if your scientific software uses standard libraries such as LaPeX and BLAS for dense linear algebra, or a sparse linear algebra library, FFT, so anything that can be expressed in these building blocks, then you're also pretty well off, because you can then just relink your program with the GPU versions of these libraries, and maybe you have to do a little modification of source code, but it's usually not very serious. And then you can offload that to the GPU, and you should hopefully get quite a good performance boost. Option number three, some programming languages support GPUs internally. So, and this is something that that is becoming more and more available, or more and more implemented in various languages. So, say MATLAB comes with GPU arrays, where you work with objects, and you can just use, say, plain arithmetic on these objects, or mathematical functions, and MATLAB automatically puts everything onto the GPU, takes care of the memory transfer, all these things for you, and you program GPUs without actually having to think about what you're doing there. So it's a pretty nice option. The same thing with Python, with CuPy. I haven't tried this out myself yet, but CuPy is a NumPy lookalike. So it does similar things or it basically uses the same API actually as NumPy, but runs things on the GPU for you. If you like C++ and Fortran, they support offloading now directly as part of the programming language. And if you have a compiler that supports this, like the latest NVIDIA HPC SDK, you can offload your workloads directly to the GPU, again, without having to think about how the GPU actually works. Then option number four, if your program is written in C, C++, or Fortran, then OpenMP 4.5 or OpenACC might be for you. So this is a way of programming GPUs where you just take your plain C, C++ Fortran program, and you annotate the loops, giving the compiler instructions and telling it to take the loop, compile it for GPU, and run it on the GPU. It does require a bit of refactoring normally. So unless your loop is already written in a way that it can be digested by the GPU. So keep in mind the GPU is a parallel thing, right? So you need to express your loop in a parallel way so that the different loop iterations can be computed independently of each other, at least ideally. But once you've done that, then the OpenMP or OpenACC compiler will happily take that and put it onto the GPU for you. And then option number five, so that's the most laborious option, but it is for you if you really want to squeeze the last flop out of a GPU. That's using the very low level programming models. So there's CUDA from NVIDIA, there's OpenCL, we support both of those. There's also HIP from AMD and Vulkan Compute. We don't support that at the moment, but these are specialized say, programming models and programming language flavors where you can program the GPU directly. Keep in mind that you will have to fork your code, which is not good for all projects. So you have to rewrite some parts of your code specifically for this, and it will also lock you in to some degree. So say if you use CUDA, that means you can only run on NVIDIA hardware. So there's drawbacks to that, but you get the best possible performance at least if you write your code well. Okay, so a few examples of what has been done over the last couple of years or so with GPUs on NeSI. So here's a case of NAMD. So that was work done by Dr. Wanting Zhao at Victoria University of Wellington and around protein modeling. That's an extremely computationally expensive problem. And here, GPUs could simply be used by downloading the container from NVIDIA. So once again, this is just an image file that you download. You put it on the HPC and you start running. And to give you an idea of how much performance you get, so for the older generation of Pascal P100 GPUs, these are now probably good 4 years old, that's the hardware design. The performance is about equivalent to 120 cores of Intel Skylake, which is a pretty recent processor. It's a pretty recent CPU, that is. And we also tried it out with the new A100s, which is the latest hardware from NVIDIA. And you get a little bit of a performance boost. It's not for that particular code. It doesn't support GPU as well as it could. So that's still under development, keeping in mind that writing code for GPUs is not always easy depending on your problem. So it can sometimes take a while and several iterations of code releases to get really a very good performance. But using the A100s, you still get a little speed boost over the P100s, even though it's not much. Here's another example. So that's also with software that supports a GPU directly. So that's a deep learning toolkit called FairSec that was used for a natural language processing project with Ximing Bao from the University of Auckland. And we didn't try this on CPU. You can do deep learning on CPU for sure, but it won't be anywhere near as fast as GPU. So that's why most people go straight to the GPU with that. And we compared the A100s with the P100s, and the newer hardware comes out about twice as fast for the small deep learning batch size. Small because the P100 has much less memory, so it's limited to something like 16 gigabyte, whereas the A100 now comes with 40 gigabytes that allows larger batch sizes. And that means that, so now thinking again of what I said before, you have to give the GPU food. So it really needs a lot of it to really show its power. And you can see that here. So if you increase the batch size, you feed the GPU with lots of data, and now it's 10 times faster compared to the case of small batch size. Another example here, that's a classical simulation. So that's a tropical circulation model that was developed by Dr. Gilles Bellon from the University of Auckland. In his case, the dominant bit was matrix multiplication. So that could be expressed by using BLAS. So BLAS is the basically linear algebra subsystem. So that's a set of routines used for dense linear algebra, and here specifically matrix multiplication. So we just basically relinked the code using the NVIDIA CUDA version of BLAS, and the matrix multiplication itself, so just the matrix multiplication, came out 1.4 times faster than 16 cores, or is roughly comparable to about 32 cores with the P100. And last example, this is some big data analysis done by Dr. Damien Mather at the University of Otago. In his case, the problem was dominated by the calculation of the log determinant of a very large matrix. So this particular algorithm that he used is not implemented in the LAPACK linear algebra library, so it had to be done with custom code and using OpenACC directives. So this kind of annotating and instructing the compiler to put the code into the GPU gave a 13 times speed up over a single core, or a similar performance to about 40 CPU cores. And now going to the A100s, you get quite a significant boost. So it's 3 times faster than the P100. just by changing the piece of hardware. So you don't actually have to change the code, and keep that in mind. So it's really just going from one piece of hardware to a newer one, and you get a 3 times boost. Okay, now I've answered the question already, so but just to give you all the details about this. So of course we have the P100, surprise. So these GPUs have been around for a number of years now. So you see it here and at the top. So as I said earlier, it's a card that sits in a compute node in the data center. And it's important to point out that these GPUs that we have are different from the typical consumer GPUs that you get for gaming. So the GeForces and the likes. And one of the differences is that the data center ones support double precision mathematics. If you do deep learning, you don't care about double precision, you want half precision or something like that. But if you do classical simulations, double precision can be very important. So it's basically a high precision kind of mathematics, and you can run double precision on GeForce, but it will be really, really slow. GeForce doesn't support that in hardware, but the data center GPUs do. So that's one of the differences. Typically, you also get more memory on the data center ones, and then memory correction and all these kind of things. But for simulations, you probably care most. If you do classical simulations, you probably care most about the double precision. So the P100s are a few years old, yes, but as I hopefully demonstrated with the examples that I showed just a few seconds ago, they are still very powerful GPUs that are a lot faster than CPUs for say smaller scientific problem sizes, smaller machine learning workloads. If you don't have the fully complex models or small amounts of training data, you can use these P100s very effectively. You'll also find that some of the older releases of software don't have support for the A100s and its additional features, so you might actually be stuck with the P100s. Now the new kids on the block here are the A100s, of course. So we will do our grand unveiling very soon. So they're not available yet, but they will be very soon. And as I said earlier, that's the latest stuff from NVIDIA. Comes with loads more compute cores. So the compute performance doubles for traditional simulations. It comes with tensor cores. It's not the first GPU to have tensor cores, but so that was introduced a generation earlier, the generation that we skipped. But for us, it's the first time that we have these tensor cores. And these are specialized little compute units that do matrix multiplication. And that's something that you really care about when you do deep learning and the likes. That's where the computational performance sits. As I also mentioned before, they have lots more memory, so you can run much larger problems on them. One particular thing about the A100 is that it introduced GPU partitioning. That means that a single physical GPU can be sliced into up to 7 pieces. And these 7 pieces can be used by several people at the same time for different workloads. And that points to the fact that these GPUs are really powerful. And a lot of codes cannot actually scale up to the full GPU. So of course you still get the performance boost if you use the entire GPU for yourself, but you can't use all the power effectively. And so it can be very attractive to slice it up and multiple people get a fraction of the GPU and still run very fast. So that's the idea behind this multi-instance GPU or MIG mode. And so, of course, what you do with that is you run much larger problems. So, we observed in our testing, we observed 2 to 3 times faster performance compared to the P100s. And if you have complex machine learning problems or if you need lots of memory. Okay, so if you're excited about this, then please follow us on social media, so on Twitter or on LinkedIn, or you can subscribe to the mailing list, and then you'll get the announcements of when these GPUs will be available. So we only make them available for machine learning projects initially because of the fact that with the tensor cores and the big memory and so forth, machine learning will really benefit the most from these GPUs, but we will make them available for all users later on. But initially it will only be machine learning projects. And so if you have a machine learning project and if you're interested in trying out the A100s, then please email us at support@nesi.org.nz and then ask for access. Okay, now continuing with the whole topic of access. So if you don't currently have an allocation for compute on NeSI, then you can get one via our web portal. So at nesi.org.nz/apply. One thing to keep in mind with GPUs is that using a GPU costs you more per hour than using a CPU. So there's a factor of 14 on Mahuika. And so that means that if you get a certain amount of compute units, so that's, which is our measuring unit for calculating how much compute you get, then every device hour will be multiplied by 40 if you use a GPU. So that means it is only really effective to use a GPU if you can use it efficiently. If you can't use it efficiently, you'll pay a high price or you deplete your allocation much quicker if you use a GPU. And so there's something to keep in mind, but we can help you work that out. So if you're unsure about your workload, then please talk to us and we'll help you with that. And so a CPU in comparison costs you roughly 1 compute unit per core. It's a little bit more complicated. I won't go into all the details. If you want to read up on that, we have a support page, and the link for that is also in the Google Doc that Megan posted on the chat before. If you have an allocation on the Maui supercomputer, you can use Maui Ansel with GPUs. That's included in your allocation. So we have, I think, 5 GPUs that you can access there. And you can run pre and post processing workflows that include GPU. I can't say much about the A100 pricing that's coming soon. That will be revealed along with the GPU launch. And almost at the last slide now. So if you already have an allocation and you're ready to go, using GPUs is really super easy. So if you use Slurm in batch mode, so if you push off your jobs to the queue, just add the line saying GPUs per node using, say, 1 or 2 GPUs. We have up to 2 GPUs per node. And so you instruct Slurm to choose a compute node that has a GPU in it, of course. If you want to use GPUs for interactive access, which is really great, say for machine learning, then you can also do that. Just launch an SILOC, so requesting interactive access to a node, and asks for, say, 1 GPU per node. And a third option for those that like Jupyter notebooks, we also have GPUs available there. So just jump on jupyter.nesi.org.nz, log on, and then when you select the resources that you want for your session, just choose GPU, and you'll get one of those. And last slide, just a little bit of advertisement. So together with my colleagues, Chris, Alex, and Maxime, I'm a consultant for NeSI. We run a computational science consultancy. That means we help people who want to run faster, better, more efficiently on NeSI. And that includes also porting code to GPU. So if you're unsure how to do that, then please talk to us and we can set up a project. If you work for a NeSI collaborator institution, working with us will probably be free. And that's pretty much it from me. Thanks very much for listening.
All right. Thanks, Wolfgang. Really fantastic. And there's been some chatter in the question document. I see Chris is busy answering some questions underneath the text in the document, but maybe you want to speak to any of those in case people haven't looked at the question document.
Okay, so I'll bring up the question page. I hope you can see the Google Doc. You can make it slightly larger to make it a bit more readable.
That's a good idea.
Okay, so the first question was, why does the GPU need to be a coprocessor? Answer, GPUs don't run an operating system themselves, and it's only really easy or makes sense to program GPUs for massively parallel tasks. Hence, they're used as a coprocessor. Anything a GPU can do, a CPU can do too, albeit potentially a lot slower, but not necessarily vice versa. Yes, I think I can probably, I think I don't have much more to add. So once again, GPUs are really specialized things. They are made for compute, so they're not very good. Say you wouldn't run an email program on a GPU, that wouldn't work, or they couldn't easily run an operating system because they simply lack abilities, they lack instructions in the hardware that you need to do to run an operating system effectively. so that they're really only meant to do numerical computation. Could you please go over the distinction between 2 using a GPU with a package container and 3? The programming language supporting GPU is their preference. Using a GPU with a package or container means the software you're using already supports GPUs. This is the easiest way to use a GPU as there's very little work to do. If the software you are using does not support GPUs already, then you would have to add support using one of the GPU programming languages approaches, CUDA, OpenACC, etc. Yeah, so just quickly expanding on this, it really depends on your project. So if you use say a community code or an open source tool like TensorFlow or something like that, then there's no need to try and program GPUs yourself, because it comes with everything included what you need. But if you have a project that you would like to accelerate computationally, or if you start a new project, it's really worth thinking about the way you want to go. So say if you really like Python, and if it makes more sense for you to use Python or say MATLAB, you could think about using one of these toolkits like CuPy or the GPU toolbox in MATLAB right from the start, and write your code so that it runs on the GPU. Or if you want to write your code in C, C++, Fortran, you could think about how you structure it so that you can use things like OpenMP or OpenACC. Or if you have an existing code, you can refactor a bit and add it on. I hope that this answers the question. The next question is with regards to MIG. And does that mean that normally access to the GPU is exclusive to a single user at a time per physical device? And the answer is the way things are configured currently, yes, GPU access is exclusive to a single user at a time per device. We're currently investigating using MIG for workloads that can't fully utilize an entire A100. So yes, so also just quickly expanding on that, normally you get the full GPU for yourself. And you run your kernels. So kernels are the pieces of code that do the computation on the GPU. In some cases, you can get virtualized GPUs. That's the older way of doing that. We don't have that on NeSI, but the older way was to time slice a GPU so that everyone gets a time slot, and then the GPU switches through the different users one at a time. And so now the new thing is that you divide up the GPU not in time but in space, if you wish, so that everyone gets a bit of the GPU, and you share the GPU memory in this big mode, in this MIG mode. So everyone can upload some data into the memory, and then the compute cores are sliced up for the different users. So it's something that we probably won't offer right away. That does require a little bit of consideration how to best do that, and how we can set up the resource allocation so that people can use it effectively. So we probably won't have that right from the start. The next question is, how do you currently support R users wanting to use GPUs? I understand R packages such as RPUD and GPU R have fallen out of favor in recent times. Do you link to cuBLAS instead, for example? Answers, I don't have experience using GPUs from R, but you could load an R package that supports GPUs if there are any, and use them that way. Our default R modules do not link against cuBLAS. I'm afraid I'm not really a big R user either, so I've only used R with multi-threading with CPUs in the past. So I'm not sure what the best option is on R. I mean, one thing you can always do, of course, is that you write part of the code that is numerically intensive in C++, using, for example, RCPP with an offloading compiler, so that the C++ part or Fortran, if you want that, that C++ or Fortran code is then offloaded to the GPU. But writing code directly in R is something that, yeah, I would have to look that up. Sorry, I can't really add much more. Oh, there's, I think one user is answering that. Okay, so I guess that is, so in the specific case of dense linear algebra with the BLAS library, so then you can use the CUDA version to accelerate these parts at least. So this is not the entire code then, or not necessarily all of the computational heavy parts, but the linear algebra bits. The next question is, could you please tell me more about using GPU with Jupyter Notebook? Is Jupyter Notebook with GPU and NeSI available to develop deep learning for video processing with Python? And Chris is just writing the answer. So you can request a P100 GPU currently through our Jupyter portal at the server options screen. So after you log on, when you select the resources that you want, you can select that you want the GPU. You can then use the GPU to do anything you like, including developing deep learning models. We have multiple Python kernels available. More info about Jupyter is available on our support pages. So yeah, basically what you do is you could say use TensorFlow or PyTorch or something like that with GPU support enabled. So you load that into your environment with a Python import, and then you can run your training workloads directly on the GPU. And here Gabriel answers these ways to use NGC containers, which have Jupyter Notebooks integrated. Although that's, I guess you probably can't easily integrate that with our Jupyter offering, but you can probably run that separately from that on the HPC. Okay, so the person who asked the question is extending the question a little bit. I'll come back to that in a moment. And the next question was, I've been using Numba to speed my Python code of recent, and I know Numba does offer GPU support, but I've yet to be successful in using Numba with GPUs. Would love some guidance, help with that if NeSI feel like exploring more. And yeah, so as Chris just wrote, we would definitely be interested in working with you. So you could write an email to support and describe your problem. And then depending on what exactly needs to be done, one possibility would be to do this with a consultancy. I haven't tried this out myself. I've used Numba with CPUs, but not with GPUs. But it's certainly an interesting use case. Do you know if New Zealand's weather and climate simulations will use GPUs in the future? I would say yes, probably. So at the moment, so at NIWA, we run the weather and climate simulations using the unified model, which is developed by the UK Met Office. And there's currently a very large effort underway to replace the unified model with a new code called ELFRIC. And ELFRIC is meant to be platform agnostic, so that means that it should be able to run on all kinds of compute hardware, and that includes GPUs. So I don't know for sure what will happen around this, but looking at the way things go, so the current developments in the supercomputer space, I wouldn't be surprised if we will be running weather and climate simulations on GPUs. So I would say probably yes. And so now going back to the previous question, or the one before that. Okay, so that's something about a server error. I can't really say much about error 500, but so if the error persists, if you can't get it to work, then please feel free to contact us over support@nesi.org.nz. So we should be able to sort you out.
Cool, great questions. Love all the different aspects that we've been able to cover. Are there any other questions or comments? Well, we appreciate you taking the time, Wolfgang, to explain GPUs to us. I'm just having a look at the document to make sure no last minute questions are being entered in. Would you have any final comments before we sign off for today, Wolfgang?
I think that's all from my side, except that I really like to thank everyone for coming along. It's been a pleasure. And also thanks for everyone at NeSI for setting this up. So that's been really great. Thanks very much.